given an infinite line charge, which is charged uniformly with charge density rho L, the field intensity at any point, which is at a distance r from the line charge. And this unit vector is AR because it is non-standard. The electric field intensity at this point is given by rho L by 2 pi epsilon r AR, which is the unit vector along the line joining the foot of the perpendicular drop from the point of interest and the point. One very important expression for us. And the expression is same at any point on the cylinder of infinite length passing through the point of interest, having the line charge as its axis. At each and every point on this cylinder of infinite length passing through the point of interest and having the line charge as its axis, electric field intensity is rho L by 2 pi epsilon r. Please check. Then we considered infinite surface charge on a plane surface extending from minus infinity to plus infinity, with rho s as the charge density, charge per unit area, and is constant throughout, uniformly charged surface. Consider any point near it. Check it, please. The unit vector towards that particular point from the surface is with unit vector AN, normal unit vector, normal to the surface, towards the point of interest. The electric field intensity is rho s by 2 epsilon AN. We have come to a case where the field is uniform. Definitely hypothetical. Definitely hypothetical. We will not normally see infinite surface charges and all. For sure. But in this case, if you see, there is infinitely huge region on one side of this surface, and the region of equal size on the other side also. If the unit vector towards the first point is an, which is above the surface in the figure, towards this it is minus an. At any point, irrespective of the distance, the field here is minus rho s by 2 epsilon an. Actually, it is minus an. Everywhere it is same means the field is uniform field. Uniform field because in this region, the field is everywhere same. Field intensity is same. Field intensity being a vector, same says it is same in magnitude and direction at each and every point on each side of this infinite plane. I gave you a set of statements that any charged object creates magnetic field or flux lines, and these flux lines are on the surface of the charged object. These flux lines or field lines are perpendicular to the surface at each and every point, because of which it is also called as normal flux. And in this normal flux, we saw the flux lines of a positive charge going radially out. Flux lines of a negative charge coming and radially coming and terminating on the negative charge. And the number of lines that normally is given by the amount of charge on the surface. Looking at the structure of it, this is divergent. You can see because they are going out flux. This is convergent flux. If you can see, both have spherical symmetry. You agree with this? Spherically symmetric. Spherically symmetric, if you consider a sphere of radius r having the charge at its center, at each and every point on it, the flux density is same. In fact, you have to see that because the flux density and the field intensity is inversely proportional to r here, when the distance between the lines is small, the field is strong. When it is more, the field is weak relatively. As we move out, the distance between the lines increases, and we say, the field intensity will decrease. And we saw one case where one is positive charge, another is negative charge, in which the field is divergent at the positive charge and convergent at the negative charge. Correct? Or in the case of both positive and both negative charges, we saw that the field lines are like this. With arrow marks going out. If it is positive charge, the flux lines, this is the flux line structure. For negative charge, they are reversed in their directions. You can see that the field lines are crowded at some place, right? And they are rarefied at some other points. These two are symmetries. No, there is no symmetry in the field in the next two cases. But still, all the fields are non-uniform. Examples of non-uniform fields in general. All are in which the field intensity is in general different at two different points. Maybe there are some points where it is in the same direction here. Here, in this case only, third case only. But still, in general, they are different. If the field intensity is different in magnitude or different in direction, as a vector, it is different. At any point, the field intensity is proportional to the flux density, flux passing through unit area, I told you. If it is non-uniform, it is different. Flux density is different at different points. Now, uniform field is one in which the distance between the flux lines and the direction is same everywhere, because of which this is represented by a set of parallel lines. If the flux lines in a particular field are a set of parallel lines, the flux density at each and every point in that region is same. If the flux density of the field or the field intensity of the field is same everywhere in magnitude and direction, we say such field as uniform field. Yesterday, I spoke about the flux created by a charge. Any charged object charged with q coulombs creates q coulombs of flux. That normally resides on the surface. That normally resides on the surface. And sends the flux lines out in the direction perpendicular to the surface at each and every point, if it is positive charge, normal flux. And if it is negative charge, the flux lines from infinity they come, or from somewhere they come, and normally get terminated onto the surface. Positive charge acts as the source of flux lines. Negative charge acts as a sink of flux lines. All those things I spoke. At any point when you draw the flux lines, if you consider a normal surface perpendicular to the flux lines, flux per unit area on that surface is called as flux density. That will have a direction. Flux density by epsilon of the medium will give me the field intensity. Now, check it properly. If I have infinite line charge, I will magnify it and show that any infinite line charge is a cylinder of 0 radius. You agree that? Line is in space is a cylinder of 0 radius. This is having the charge of charge density rho L. This goes to plus infinity like this. And minus infinity. One thing is sure for us. Even before deriving the expressions only, we saw that if there is infinite line charge, field is cylindrically symmetric. Now, this will send the flux lines out. Correct? Let me draw anyway, no problem. The front view of it is this. Please concentrate. I just consider some length L of the charge. The front view of the flux lines created by this charge are like this. Appear to be uniform. No, it is not uniform because the top view of it will be like this, correct? Field lines are going like this. Are you comfortable with this statement? Please check. These are all really very important statements that you should know. This is the top view. This is top view. This is front view. If I consider a length L of this conductor, I'm not worried about how much length I take. Ultimately, that length is not important for us. These are the flux lines created. You're concentrating. To determine the electric field intensity at this point, I should determine the flux density at that point divided by epsilon. We know that the field is cylindrically symmetric, because of which, passing through the point of interest, we will consider a cylinder of radius equal to the distance of the point, having the line charge as its axis. The top view of it is this. Correct? Definitely, the flux is uniformly distributed on the cylindrical surface of radius Let us say R. I have taken an imaginary cylindrical surface passing through the point where I want to determine the field and having the line charge as its axis. If rho L is the charge density and L is the length of the cylinder considered, number of flux lines passing through the cylindrical surface is what? Psi is equal to L into rho L, because all the lines which are created by the charge on this length L of the line charge will go radially out and pass through the cylinder and go out. Any problem in understanding this point? L rho L is the total flux which is normal to the surface because it is radial also. And flux is scalar. The normal flux density d bar is equal to what? The curved surface area of the cylinder of radius r and length L is 2 pi r into capital L. Total amount of flux L into rho L divided by 2 pi r into L. In which direction? A radial to the cylinder is the flux density, because of which it is rho L by 2 pi r. Consider L to be infinity also, no issues for me, because anyway I will divide it for the sake of determining the flux density. D bar is equal to this and E bar is equal to D bar by epsilon is equal to rho L by 2 pi epsilon r E r, without using Coulomb's law and integration. We could determine the expression for the electric field intensity at any point. These advantages, right? In the same way, I told you that all the derivations are carried out for vector quantities, assuming positive source, and ultimately, if the source is negative, you have to substitute the value in the formula. Please check once. Now, the second case. We consider infinite sheet charge. I will show it like this only. Sheet going like this. So the page and half above. I will just show it by a line. That's what I can see. If it has rho s as the charge density, assuming positive charge only, the charge per unit area on the top surface is rho s by 2. Charge per unit area on the bottom surface in the figure on one surface and other surface is rho s by 2. It is distributed. Charge per unit area on each side of the surface plane is rho s by 2. From this, definitely, when the flux lines come out of a plane surface in the direction perpendicular to it, they are all set of parallel lines. Now, to determine the field at any distance, I need to consider a surface of area A perpendicular to these lines. When I say I consider a surface of area A perpendicular to these surfaces, these lines, they are coming from the same area A on the surface. And the total number of flux lines passing through this surface of area A is A rho S by 2. And the flux density d bar is what? A rho S by 2 by A AN, which is rho S by 2 AN. Because the flux density at any point is rho S by 2 AN, electric field intensity E bar is equal to rho S by 2 epsilon AN. We determined actually these expressions by using the electric field intensity at any point because of a point charge as a special case of Coulomb's law, and using integration of the tool we determined the field quantities. So in these two cases we use the fact that every charged object creates flux lines at any point where flux lines equal to the charge. At any point in the region, if you draw a small surface perpendicular to the flux lines, flux per unit area on that small surface will give me flux density in the direction perpendicular to the surface. Flux density in that divided by area, flux density divided by epsilon will give me electric field intensity. Using that also we could determine. These two are in normal electromagnetic subject books, are given in the list of applications of Gauss law before going into Gauss law. Please check. If the given source of electric field is a hollow cylindrical surface of radius A, at least hypothetical case of any length, infinite length or finite length, we could determine, given the line charge density, the electric field intensity at any point through integration for a conductor of length L by 2 L also. That is filamentary conductor, which is the cylinder of tending to 0 radius. If the conductor is a cylindrical surface, hollow cylinder, it's a surface now of line charge density rho L per unit length of this surface, rho L. Normally, it is not the line charge that we basically talk about here. It's a surface. Rho S is the surface charge density. Please check it. If the radius of this is A, rho S into 2 pi A, the length 1, or length delta L we take. 2 pi a delta L is the charge on the surface divided by delta L, rho s into 2 pi a, is the charge per unit length of vector through surface charge density rho L. Anyway, it is not rho L because it is a surface. What I really want is rho s. Given rho L, I will find out rho s. Given rho s, I can basically talk about per unit length of the cylinder, how much charge is there. Please check it once. My question is this. It's a cylindrical surface. Is it possible to determine the electric field intensity at any general point, inside or outside? Is it possible for us to determine the electric field intensity at any point due to this charge? Essentially using the integral, double integral of rho s ds into general r bar divided by 4 pi epsilon into mod r bar whole cubed. Can I determine the expression for the electric field intensity at this point using this integral rho s into ds by? Can I? It is nearer to impossibility because it's extremely difficult. Maybe ultimately you should leave it if you try to derive it, because the surface itself is a cylindrical surface. We need to get into cylindrical coordinate system. Whenever we want to use cylindrical coordinate system to determine the field at this point from any general point on the surface, we have to consider dx, and from the ds we need to define a vector to the point of interest. That means I should be in a position to mathematically write the vector from any general point on this cylinder to the point of observation where I want to determine the field quantity. It is not possible. It is not possible because the direction of arrow is different at different points. I told you that in curvilinear coordinate systems in which one or more surfaces are curves, the directions of unit vectors are not unique, because of which a general vector from any point to any point is not defined. Since it is not possible to define, a general vector or bar cannot be defined. So we cannot use this integral to determine the electric field intensity. In the same way, if we consider a spherical surface of radius r on which the charge is present, it is not possible by using the integral, because it is a surface charge again. Why it is not possible? The natural coordinate system, leave alone, leave the Cartesian coordinates forever when the surfaces are cylindrical and spherical. If we get into the spherical coordinate system, I should be in a position to define on the sphere, the vector from any point to any point on the sphere, not defined, not given in spherical coordinate system. In this case also, R bar is not defined, because of which I cannot use this. But we need the electric field intensity at any point due to a cylinder, charged cylindrical surface, charged spherical surface, and moreover, volume also. Charged volumes, normally not possible, but still we say hypothetical case. In all these cases, we use something called as Gauss law.